All right, so get ready for another deep dive. This time, we're taking a look at the Riemann Zeta function. And get this, we're going visual. That's right, we're going to explore this complex mathematical concept through 3D plots, contour maps, and even polar projections.
What always gets me is how visualization can help us see patterns, especially in these really complex mathematical concepts. It's like we're looking at something familiar, but in a completely new way.
Yeah, for sure. Okay, so before we get too far, what exactly is the Riemann Zeta function? Because it sounds kind of intimidating, if I'm being honest.
Well, it's a function of a complex variable, which is often denoted as phasors. And you can think of a complex variable as a number, but with two parts, a real part and an imaginary part. So it's like having coordinates on a map, but instead of north, south, and east, west, you have real and imaginary direction.
Okay, I think I'm following so far. So what is the function itself?
So the function itself is a sum of an infinite series.
Okay, an infinite series. I'm already feeling a little lost.
But what makes it so interesting is that it's connected to prime numbers. You remember those, right?
Oh yeah, prime numbers. Those are the numbers that are only divisible by 1 in themselves.
Exactly.
Yeah, I remember those from school. They always felt a bit magical. But how are prime numbers related to this function?
So that's where Euler comes in. He found this amazing relationship that's expressed in what we call the Euler product. And it basically shows that the Riemann Zeta function can be represented as a product involving all the prime numbers.
Wow, okay.
So this connection basically suggests that the function might be able to tell us some really deep secrets about how prime numbers are distributed. Secrets that mathematicians have been trying to uncover for centuries.
Okay, so the Riemann Zeta function is a way to represent prime numbers. And by studying it, we might just unlock some of their secrets. But you also mentioned a mystery. What's that all about?
All right, so this function, which seems so simple, also has something called zeros. And you can think of them as specific points, like on a map. In this case, the map is what we call the complex plane. Now, there's some zeros called trivial zeros, which are pretty easy to understand. But then you have these non-trivial zeros, and those are the real head-scratchers.
So these non-trivial zeros are really important then?
Absolutely.
Why is that?
Well, the Riemann hypothesis basically says that all of these non-trivial zeros, they all lie on a specific vertical line in the complex plane.
A vertical line? That seems almost too simple.
I know, right? But it actually has huge implications. Imagine this infinite plane of numbers. Trying to find these zeros is like searching for these tiny little points within this giant plane. And if the hypothesis is true, then they all line up perfectly. It's pretty mind-boggling. Proving this hypothesis would change how we understand number theory and how we understand the distribution of prime numbers.
So this seemingly simple idea, all these zeros on a line, this could unlock all these secrets about prime numbers and how they're spread out or distributed, as you said.
Exactly. It's a really big deal. In fact, it was even included in Hilbert's famous list of unsolved problems. You know, those 23 unsolved problems in mathematics. And get this, it's one of the Clay Mathematics Institute's Millennium Prize problems. If you solve it, you win $1 million.
$1 million? Wow, now I see why it's such a big deal. Okay, but if this function is so complex, how do we even begin to visualize it, let alone find its zeros?
That's where it gets really interesting. So the Riemann Zeta function, it's actually a four-dimensional object.
Yeah.
And our brains, well, we can't really grasp 4 dimensions directly, so we have to get a little creative.
Okay, so how do we do that?
That's where the research we're diving into comes in. It uses techniques like 3D plots, contour maps, and even polar projections, all to represent different parts of the function.
So these visualizations are more than just pretty pictures. They're actual tools that mathematicians can use.
Exactly. And they can help us understand how the function behaves, and might even give us clues on how to solve the Riemann hypothesis.
Okay, my mind is already blown. Let's get into the specifics. What can we actually see in these visualizations? What kind of patterns are we talking about?
Well, let's start with contour maps. Imagine a topographical map, but instead of mountains and valleys, we're showing the values of the Riemann Zeta function across this complex plane. Different colors and lines show how the function's value changes, kind of like a mathematical landscape, but with colors.
Ooh, I like that, a colorful mathematical landscape. So where do the zeros fit into all of this? Are they like hidden valleys or something?
They're even more interesting than that. These contour maps show us something called ribs. And these are lines where the function's phase abruptly jumps. And think of the phase like an angle, telling you which way this complex number is pointing. And the location of the zeros, it's often connected to these ribs.
Hold on, so the zeros kind of leave these telltale signs, these phase jumps on the contour maps, like they're leaving breadcrumbs or something?
That's a great way to put it. And it gets even cooler when we look at 3D plots. Now, these are a bit more complex. So
Mm-hmm.
So in a 3D plot, we take the function's real and imaginary parts, and those become like the x and y axes. And then the z-axis, that's either the real or imaginary part of the complex variable itself. You can almost imagine it like a path twisting through space.
Oh, okay, I'm trying to picture that. So where do we see the zeros in this 3D plot?
Well, they're the points where the curve intersects with itself. And remember how we talked about the Riemann hypothesis?
Yeah.
Well, if it's true, then all these intersections, they should perfectly line up along a specific plane. And that plane corresponds to that critical line we talked about.
So you can actually see the hypothesis visually. That's amazing. Okay, but you also mentioned something about polar projections.
Right.
What are those all about and what can they tell us?
Now, this is where things get really interesting and maybe a bit weird. Imagine taking that twisting 3D path and like projecting it onto a flat circle, like shining a light through a coiled spring. What you get are these, well, some researchers describe them as snail-like shapes.
Snail-like? How can a math function look like a snail?
It all comes down to how we choose to show the data. So in these polar projections, we use the magnitude and phase of the complex variable to determine the radius and angle. And for certain projections, you start seeing these snail shapes pop up. And they usually appear near the zeros of the function. But, and this is the cool part, the direction these snails point seems to flip-flop at consecutive zeros.
Wait, so these snails are like little signs pointing us to where the zeros are. That's wild. But out of curiosity, why snails? Of all the shapes, why snails?
You know, that's a good question. And part of the mystery, I guess, is just this pattern we see in the math, but we don't really know why it looks like that. It's these kinds of weird and unexpected patterns that make exploring complex math so fascinating.
I can definitely see that. So these snail shapes and these phase shifts, do those patterns help us find the zeros?
Yeah, they actually might be able to predict where the next zero could be.
Yeah.
And we might not even have to do a bunch of complex calculations to find it.
That's incredible. So these snails are kind of leading us on a treasure hunt, with each twist and turn pointing us towards the next zero.
I like that analogy.
Okay, but if these patterns are so helpful, why haven't we figured out the Riemann hypothesis yet?
Well, that's the million-dollar question, isn't it? The paper we've been talking about, it mostly focuses on looking at the zeta function for small values. Small values of the complex variable, that is. So it's very possible that as we look at larger values, things could get a lot more complicated, like exploring uncharted territory.
So the deeper we go, the more complex the landscape becomes. But could there be limitations to using this visual approach? After all, we're basically trying to look at a four-dimensional thing with our three-dimensional brains.
That's a valid point. Visualizations are really helpful, but they are just representations. They're not the real thing. So there's always a chance we could oversimplify things or misinterpret what we see. But I think the real value here is that these visualizations get people asking new questions, and they're encouraging mathematicians to think differently about the Riemann hypothesis.
That makes sense. So they're giving us a new way to, I don't know, see the math in a way.
Yeah, like that.
Okay, but how about the more practical side of all this? How are these visualizations made? Are we talking about like supercomputers working nonstop for days?
It might surprise you, but they're not as complicated as you might think. Obviously, we use some fancy software, but the basic idea is pretty simple. Remember those infinite series we talked about earlier? Well, computers can calculate those series, but only up to a certain point. So we get an approximation of the function's value, but just at a single point.
So it's like taking a snapshot of the function at one specific spot.
Exactly. And then we do that for a whole bunch of different values. And that gives us a data set that shows how the function behaves, at least in a certain region. And then we use different visualization techniques to turn that data set into those contour maps, 3D plots, and polar projections.
It's amazing that we can take something as abstract as the Riemann Zeta function and actually see it on a computer screen. But even with all these tools, the Riemann hypothesis is still a really tough problem to solve. What are some of the biggest challenges researchers are facing?
I think one of the biggest challenges is just the complexity of the Riemann Zeta function. As we look at higher values of the complex variable, the function's behavior just becomes more and more complicated. It's like trying to explore a dense jungle. The deeper you go, the harder it gets to find your way around.
So it's not just about finding the zeros, it's about understanding the bigger picture. It's like trying to learn the language of the jungle to figure out how it all works. But haven't mathematicians already found tons of zeros that fit the Riemann hypothesis? Doesn't that mean it's probably true?
It definitely provides strong evidence. But in math, even finding a million examples doesn't mean something is always true. There's always the chance, however small, that there's a counterexample out there somewhere, maybe lurking somewhere in the complex plane, beyond what we're able to calculate right now.
So it's like searching for a needle in a haystack, a needle that might not even exist. But with all the progress in computing power, surely we're getting closer to figuring this out, right?
Yeah.
We're back, and I don't know about you, but I'm still thinking about just how big this Riemann hypothesis is. It really feels like we're looking at the foundation of numbers, you know?
Yeah, for sure.
But you mentioned advances in computing power, so we must be learning more all the time, right?
Oh, absolutely. Computing power keeps getting better and better, and that's letting us explore the Riemann Zeta function in ways we couldn't before. We can generate huge data sets and see things in the visualizations that we couldn't see before. But more and more people are realizing that computing power alone might not be enough to solve this thing.
So we need new ideas, new ways of approaching the problem. It's not just about crunching numbers, but about having that aha moment, that flash of insight. Where do you think those new ideas will come from? Could these visualizations themselves be the key?
That's what's so cool about this whole thing. These visualizations, they're not just tools, they actually spark creativity.
Yeah.
By showing the Riemann Zeta function in new ways, mathematicians are starting to ask new questions and explore new connections, you know? Who knows, maybe the next big breakthrough will come from someone looking at a snail shape
Yeah?
and suddenly seeing a pattern that everyone else missed.
Yeah. It's like these visualizations help us connect the abstract world of math to the visual world that our brains can understand.
Exactly.
Okay, but let's move beyond just the pretty pictures. What are some concrete things researchers have learned from these visualizations?
Well, one of the biggest things has to do with those non-trivial zeros and how they're spread out. Remember the ribs we talked about on those contour maps? Researchers have found that the spacing between those ribs is surprisingly regular, even when we look at really high values of the complex variable.
So there's some kind of order to it. It's not just completely random.
That's what it seems like. And that regularity is really important because it suggests a connection to other areas of math, especially something called random matrix theory.
Random matrices, that sounds even more complicated than the Riemann Zeta function. What do those have to do with this?
Well, it turns out that if you look at certain types of random matrices, the spacing between their eigenvalues has a similar pattern to the spacing between those ribs on the contour maps of the Riemann Zeta function.
Wow, okay.
This connection has been really helpful for understanding how the zeros are distributed. Random matrices have been used to study lots of complex systems in physics, and now they're giving us insights into prime numbers.
So there's this hidden link between random matrices, which seem chaotic, and the structure of the Riemann Zeta function.
Exactly. It's like finding a secret passage between two completely different worlds.
I love that analogy. And this connection has led to a lot of new research, right?
Yeah, tons.
Yeah.
Mathematicians are now looking at ways to use the tools from random matrix theory to try and solve the Riemann hypothesis.
So it's like having a whole new set of tools in our mathematical toolbox.
Exactly.
Okay, this is truly amazing. But beyond how the zeros are distributed, what else have we learned from these visualizations?
Another really cool area has to do with the phase of the zeta function. Remember we talked about those phase plots and how they showed sudden shifts at each zero?
Yeah.
Well, it turns out those phase shifts aren't random. They seem to follow very specific patterns that depend on where the zero is.
So it's like each zero has its own unique fingerprint.
Yeah, exactly. And by studying those fingerprints, we're starting to understand more about the structure of the zeta function and how it's connected to prime numbers.
This has been a really mind-blowing journey. We've covered so much. From the basics of the Riemann Zeta function to how we can visualize it and all the cool things we've learned from those visualizations.
It's a great example of how, even in abstract math, there's always something new to find.
That's for sure.
And who knows, maybe one of our listeners will be inspired to make the next big discovery.
Maybe they'll be the one to crack the Riemann hypothesis. But seriously, this has been a fascinating look at the Riemann Zeta function. And for those of you listening, we'd love to hear your thoughts. What surprised you the most? What questions do you still have? Share your ideas with us. You never know, you might just spark the next big breakthrough. Until next time, keep exploring.